All right, so the first thing we're going to do in this chapter is we're going to do simplifying radicals. They give the definition there for any real numbers a and b and any positive integer n. If a to the n equals b, then a is the nth root of b. The radical sign indicates a root. The expression under the radical sign is called the radicand. All right, so they give a picture there to the right. You'll see that you should be familiar with this root here. We're used to square roots. That is called the radical or the radical sign. Inside, what you are taking the root of is the radicand. An index that tells you which root you are taking. If there is no index, you're taking the square root. Like square root of 9 is 3. What multiplies twice to get 9? It's 3. Other than that, you're going to see an index there. All right, you're going to see some root to indicate what you're taking the root of. Some things about roots. All right, they give examples here. What does this mean? Well, if I have 3 squared, that equals 9. We all know that. This is what it looks like the other direction. The square root of 9 equals 3. 3 cubed is 27. The cubed root of 27 then is 3. 3 to the 4th is 81. The 4th root of 81 is 3, so on and so forth. All right? And so you can really have any root. It just says how many times do you multiply that number to get to the number on the inside. A couple things about the numbers here. If b is greater than 0, that means if the number you're taking the root of is positive, all right? And you have an even index, square root, 4th root, 6th root, you will have 2 answers. It could be positive or it could be negative. For example, if I have x squared equals 9, I have to consider the fact that x could be positive 3 or negative 3, okay? Now, typically when you see this sign like this, they want what's called the principal root, which we'll talk a little bit about, which means they want you to match the sign on the inside. But if you have a variable involved, they want you to consider all possible roots, okay? And so when it's even, you have to consider a positive root and a negative root. If it's odd, so in this example, we have 27 in here. That's a positive number. We have an odd index, 3. You're only going to have one answer. Negative 3 won't work because if I do negative 3 times negative 3 times negative 3, I would get negative 27. I wouldn't get positive 27. So if I have an odd root, an odd index here, I'm only going to have one answer. Okay? I'm only going to have one answer there. And it's going to be positive if the inside is positive. If what you're taking the root of equals 0, your answer will always be 0. All right? So no matter what root you're talking about, the root of 0 is always 0. All right? If b is negative. If b is negative and you have an even root, square root, 4th root, the answer is it's undefined. You have no answer if we're talking about integers. If we're talking about real numbers, okay? So for real numbers, you will not have an answer. It's an imaginary. And so for this particular piece, you're going to say it would have to be imaginary. We have no real roots. If b is negative and it's odd, then you're going to have one negative root. Had this been the cubed root of negative 27, my answer would have been negative 3. All right? And so these are just some of the rules of finding roots. So let's look at some examples. Top of page 289. Find each real number root, so that's important. If no real root exists, state that it does not exist. So let's look at this first one. They want the cubed root of negative 125. We're just going to say what multiplies 3 times to get negative 125. Well, this is going to give us negative 5. It is a negative radicand. My index is odd. My answer should be odd. If I look at b, however, I have a negative in here and an even root. Well, this does not exist. So we have no solution here as far as real numbers go. Let's look at decimals. All right? This is the square root. If this were just 16, I would say it's 4. However, I have decimals. So I have an even root and an even number of decimals. All right? And think about how decimals work. You multiply and you add up the number of decimal places. Okay? So this has 2 decimal places. If I'm taking the square root, my answer should have 1 decimal place. And so I'm just going to look at this like, well, the square root of 16 is normally 4, but 0.16, it is going to be 0.4. 0.4. Let's look at fractions. Fractions. With fractions, you just consider the numerator and the denominator. In fact, you can do them individually. So if I'm doing this one, I could say, well, I can look at the cubed root of 27, and I can look at the cubed root of 8. And those both have perfect cubes. 27 has a perfect cube of 3. 8 has a perfect cube of 2. Okay? And let's look at the last one. All right. So for this one right here, with something with zeros, you can also do kind of the trick we did with the decimal places. You'll notice that we have 8 zeros here, and I'm taking the square root. That's just going to cut it in half. It's the same thing with zeros. If I multiply 10 times 10, I end up with an answer with 2 zeros on the end, right? So your zeros add as you multiply pretty much. And so if I'm taking the square root of something with 8 zeros, my answer is just going to be the root of this guy with 4 zeros. And there's also one more way to look at that, which we will in a second. So I say, oh, this is just 10,000, 4 zeros. All right. They rewrote it like 10 to the 4th squared equals 10 to the 8th. I don't think you're going to think to write it out that way, so you may just want to look at the shortcut when you're doing that. And then I look at my b. I always do this with my variables. I'm going to say b, and my index is 4, so I will say 8 divided by 4. So I know that 2 of my b's are going to come out. All right. This last one, even though this, I could say 12 divided by 2, potentially, right? But this is asking me to find the root. This one's going to have no real roots because that's going to create an imaginary. It would have an imaginary root of 3i and c to the 6th. But if it says asking us for real roots, there are no real roots. So there's no real for this one. For this one, 216. It's negative. It's a cubed root. Can we take a negative cubed root? We can, right? And then we look and see what happens 3 times. 6 times itself 3 times gives us 216. So here I'm going to get a negative 6 to get that, right? Let's look at this one. This is one that doesn't have a perfect root. And we're going to do some more of these. It does not have a perfect root. So there are a couple ways to do this. You can use your factor tree. All right. When I use my factor tree, I always do my primes on the left, right? I know it's just my method of doing it. And that's just so some things don't get hidden in the midst. I'm then going to look at my index in case here I don't have one, so my index is 2, which means they're going to have to group by 2 in order to come out. All right, so I have a 5 that grouped by 2. I circle that. That's my method of saying, hey, that's what's going to come out. I have a 2 that does not have another one, so I square that one. That stays in my root. All right. For these two, we're going to do more of these. I'm going to use my same method here. 15 divided by 2. That does not evenly divide. 15 divided by 2 is going to be 7 with a remainder of 1. All right? The 7 tells me how many x's come out. The remainder tells me how many x's stay in. So 7 x's will come out. 1 x will stay in. So that goes out, that stays in. I'll do the same thing with my y. 3 divided by 2. Well, that's going to be 1 with the remainder of 1. That means 1 y is going to come out, 1 y is going to stay in. So if I look at everything that I've pulled out a 5, an x to the 7th, and a y to the 1st power. What has stayed in is a 2, an x to the 1st power, and a y to the 1st power. And if you look at your answer, that's what we have. We have a 5. We have an x to the 7th and a y to the 1st power. On the inside, we have a 2, x to the 1, y to the 1. Okay? So that's how we're going to simplify these when they don't simplify perfectly. And let's look at the last one. The cubed root of 1/8 x to the 9th. Remember, you can do this individually. The cubed root of 1, well, any root of 1 is 1. So that's going to be a 1 over the cubed root of 8. The cubed root of 8 is 2. And then we can do our same method. X to the 9 divided by 3. That is 3, no remainder. So that means 3 x's come out, which is our answer there. 1/2 x cubed. So they wrote it this way, or we just have this right here. We have to use absolute value if n is even. We don't have to use absolute value if n is odd. Okay? Why does this matter? So let's look at this right here. Square root of 25, that's easy. We know what the square root of 25 is. The square root of 25 is just 5. If I look at my x, I can say, well, x, that's going to be 14 divided by 2. That's going to be x to the 7th power. All right? But this was a square root. What happens if x is negative? Even -1. Let's say I put a -1 in here, right? Then that's going to give me a negative answer. Well, I can't have a negative answer. I had a square root, right? Does that make sense? And so in this situation, I have to say, I have to force this guy to be positive. He cannot be negative because it is a square root. Had this been an odd root, it wouldn't matter if it was negative in there, right? But it matters because it was an even root. So if you have an even root, so an even index, and when you take out, you have an odd exponent, then you need the absolute values, okay? That's how this is going to work. Even index, and you take a variable out with an odd exponent, you're going to need to put absolute values, all right? Let's look at the next one. All right, so we have a negative in front. That's fine. Just leave him there. Square root of 49, well, that is a 7. Y, if I take a y, it's y to the 2nd power divided by 2. That's y to the 1st power. And then the z is going to be 12 divided by my index, so it's going to be z to the 6th power. Which of these variables could possibly be odd? Well, they both could be odd. But for this one, if I take it to the 1st power, negative, if I take a negative to the 1st power, it will stay negative, right? I can't have a negative under here. This was a square root. So for this y, I'm actually going to have to use absolute value. I don't have to use absolute value for the z. Why not?
Because it's an even number.
It's to the 6th power. If I take any number to the 6th power, it will be positive anyway. It's okay because it is a square root and it's positive. That's what I need it to be. But this guy could be negative. I can't let him be negative because I have a square root. You can't take a negative in a square root. So I put absolute value around the y because it was to the 1st power. I did not have to put it on the z because it was an even power. Let's look at the last one. Again, this is an even root, a 4th root. The 4th root of 1/16 is just 1/4. The 4th root of r to the 8 divided by 4 is r squared. And this is a group. So I leave this alone, s cubed minus 8. The 4th root of this is 20 divided by 4. This is going to be 5. Again, the r will never be negative because I'm going to square it. This is to an odd power. This could be negative in here to an odd power. Since my original root was even, I need to do absolute value around my odd power. All right? This is one that you're not naturally going to know the root for. First of all, we're taking the 3rd root, which means I don't have to worry about absolute values at all. I don't even have to consider absolute values here. But I do have a rather large number that I'm going to have to probably factor. There's a couple ways to do this. In your book, they actually tell you to rewrite it as perfect ones that divide by 3. So they take 2 to the 6th power and 3 to the 1st power. Okay, you're not going to know that's 2 to the 6th power just off the top of your head. You're probably going to need to factor it, okay? And so you're going to use the factor tree for your numbers. So for my numbers, I am going to use my factor tree. And I'm going to say, well, 2, I always start with a small prime so that my small primes are always on the left and they don't get mixed up in the middle of it, okay? And so 2 into 19, that's 9. And then with 1 left over. And then we have 2 into 12, that is 6, right? And then it divides by 2 again, or it divides by 3, whichever one you want to do, as long as you don't get it lost in there. But 3 and 32, 2 and 16, 2 and 8, 2 and 4. I'm just breaking it up, 2 and 2. Okay? Then I'm going to look at my index. My index is a 3. That's how it has to come out. It has to be in sets of 3 to come out. So I'm going to look at this and say, okay, it has to be in sets of 3 in order to come out. So I have 1, 2, 3 2s right here. Okay? So I have a 2 that's going to come out because of that. And then I actually have, and because of how I did my factor tree, they're split up, but there's still 3 of them right there. Right? 1, 2, 3. So another 2 will come out. And then I have a 3 that does not have a group of 3s. So that means the 3 is going to stay inside my radical. So inside my radical, I am going to have a 3. All right? And then I'm going to look at my variables. So if I look at the first variable, a to the 5th, I am going to divide that 5 by 3 because that was my index. All right? 5 divided by 3. Well, it goes in 1 time with a remainder of 2. So that tells me that 1a is going to come out, 2 a's are going to stay in. And so that's what I'm going to write out here. I'm going to say, well, I have a to the first power out here, a squared in here. And then I'm going to do the same thing with my b. So I have b to the 10th divided by 3. 10 divided by 3 is 3 with the remainder of 1. So that means that 3 of my b's are going to come out. 1 of them will stay in. So I have b cubed on the outside, b to the first power on the inside. Everything that you take out multiplies. Everything that stays in multiplies. So to simplify this, I'm going to say 2 times 2 times a times b cubed. So I would write that 4ab cubed. And then on the inside, it's already as simple as it will get, 3a squared b. All right? And that would be my answer. All right, so just like at the beginning, we talked about decimals. This first one is an example of decimals. We have a negative, but that is okay because it is an odd root. So I have 1, 2, 3 decimals, and it is a third root. So that means that my number that I take out is going to have 1 decimal. So I just look at the cubed root of 8. Well, the cubed root of 8 is 2. But since it is 3 decimals with 8, it's going to be 1 decimal with 2, specifically a negative 2 because it was a negative 8. So the number that's going to come out here is going to be a negative 0.2. Okay? Then I'm going to look at my variables. The x is squared. When my exponent on the inside is smaller than my index, all of them stay in because it's going to be 2 divided by 3, that is 0 with a remainder of 2. So on the inside of this guy, that x squared is going to stay put because his exponent is smaller than the index, right? Then we're going to look at the y. We can say y is to the 9 divided by 3. That is 3 with a remainder of 0, so all 3 of my y's will come out. And then for my z, that is z to the 7 divided by 3. That is 2 with a remainder of 1. So I have 2 of the z's that will come out. 1 z will stay in. And because it was a cubed root, I don't have to worry about any absolute values. All right, so we're combining all of the stuff right now. Let's look at b. All right, so for b, I'm going to take that 320 and I'm going to factor it. All right, so I'm going to say, you can do 2. 2 will go into it. So we can say 2 goes into 3 1 time, 2 goes into 12 6 times, then 0. We can do 2 again. It will go on for quite a while. All right, then I look at my index. What is my index here? Well, it's a 2. So in order to come out, I need to group it by 2's. So I have 1, 2 that will come out there. I have another 2 that will come out there. I have another 2 that will come out there. And then I have a 5 that will stay in. Those are my numbers. Then I'm going to look at my variables. X squared divided by 2. That's a 1 remainder of 0. I have an X that comes out. None of my X's stay in. For my Y, I have Y to the 3 divided by 2. 1 Y stays in. Remainder of 1 comes out. And then I have Z to the 4 divided by 2. That is 2 remainder of 0. 2 Z's come out, no Z's stay in. All right. This was a square root, so I have a problem with some of my variables. I do need to multiply these. 2 times 2 times 2 is 8. The X and Y are to the first power. That's an odd power with an even index. Those need to be in absolute values. And then the Z squared does not need to be in the absolute value. It will always be positive. And then 5Y is on the inside. That's what my answer looks like right there. All right, questions on those? All right, let's try some. All right, let's go over this last one here. So we have 625. That's the first thing I'm going to look at. Anything that ends in 5 is divisible by 5. So I always start with 5 with those. So we have 5. 5 goes into 60, or you can go one at a time. Guy goes into 6 one time with 1 remainder. Goes into 12 2 times with 2 remainder, and into 25 5 times. All right. And then we're divisible by 5 again. 5 goes into 125 25 times, and then 5 and 5. All right, so that's my factoring there. And I am looking for 4 in groups of 4, which this guy is a perfect 4th root, 5. That's where this 5 comes from. Then I'm going to look at my variables. I have a to the 5th power, and I'm going to divide that by 4. That is 1 with the remainder of 1. So I have 1a that came out, and 1a that stays in right there. And then I'm going to do the same thing with my b's. I have b to the 7 divided by 4. That is 1 with the remainder of 3. So I have 1b that stays out. That's where that comes from. 3 b's stay in. That's where that comes from. Because it was an even root 4, and I had variables with an odd power, those both had to be in absolute values. The area of a triangle. Normally we know the area of a triangle is 1/2 base times height. Hopefully you know that standard area of a triangle. However, there are times when you do not know the height, okay? Times when you do not know the height. And so this is one method of solving the area of a triangle when you do not know the height of it. The formula is S times S minus A times S minus B times S minus C under the root. That's why it's falling in here. Let's define what S is. S is the semi-perimeter. Semi-perimeter. That's just the perimeter divided by 2. That's what the semi-perimeter is. The perimeter divided by 2, okay? And so you basically find the semi-perimeter by adding them up, divide by 2, and then you just plug it in. A, B, and C are the side lengths, all right? So if we look at this first one, find the area of the illustrated plot of land, express your answer as simplified radical and as a decimal approximation to the nearest square yard. So they want you to put it in radical form, and they want you to round it. So we're going to show it both ways. So the first thing we have to do here is we have to find our semi-perimeter. So we're going to say S equals, my perimeter's just the sides added up. So I would say 81 plus 54 plus 45. To make that a semi-perimeter, I divide that by 2. So my semi-perimeter here is going to be 90. All right. Then to find my area, I'm going to just plug that in. I'm going to say 90 times 90 minus 81 times 90 minus 54 times 90 minus 45. All right. That's that right there. You would use a calculator to do all your multiplication, but you're not going to use a calculator to do your root because it's going to give you a decimal, and I need a radical first and then a decimal. All right, so let me talk to you about doing this. I would not multiply those first, all right, and I'm going to show you why. So I'm going to scoot this up so you can see this, all right? If I multiply all of those, I'm going to get this really huge number that I need to factor. But what you're looking at are factors of that really big number. Does that make sense? And so I'm not going to multiply it into a huge number and then factor it. I'm going to go ahead and factor all the little numbers, okay? And so I'm going to take this and I'm going to say, well, I have, and there's a couple ways to do this. This is 10 times 9. This is 6 times 6. This, by the way, is just 9 times 1, so we'll just drop that down there. This is 9 times 5, okay? Everybody see how I factored them? I can keep going with the factor trees if I want to. I'm gonna do it 2 ways to show you with the factor trees and without. So I immediately know I'm gonna pull out a 9 and a 6, by the way, because I have a pair there. I can see that I have 3s to pull out the 9, and if I kept factoring, I would see the 10. So you can stop here and start pulling stuff out, or you can continue to factor. So all I did was break those down, and then I'm gonna factor. I have 2 and 5, 3 and 3, 3 and 3. I'm going to run out of room. We'll drop these down. 2 and 3, 2 and 3, 3 and 3, and that is just a 5, right? Those are all my prime factors here. See that? So instead of getting a really huge number and factoring it down, I just factored all my small numbers. And then I can pair them up. So I have 3s that pair up. I have another set of 3s that pair up. I have another set of 3s that pair up. I have a set of 2s that pair up. Don't get them lost, by the way. I actually have a set of 5s that pair up, right? And then I have this little lone 2. This is why I tell you to be careful with doing it this way. I have a little 2 that's going to stay in. All right. So that's it in radical form, by the way. That's why I didn't multiply it into a huge number, because I would have had to break it down into these prime factors anyway. I just took the individual numbers and broke those down. And then, of course, you can multiply. We're going to have, 81 times 10. So we have 810 squared root of 2. That is the simplified radical form. That is the area of this in radical form, okay? Then it said approximate, so you would plug that into your calculator and round to the nearest whole number. They want the nearest yard. So if you were to plug this into your calculator and round it, then you would get 1,146 square yards. Okay? This would be exactly the same thing you would get if you had this height here and did 1/2 base times height. That's the same area you would get for this triangle if you had that height value and you did 1/2 base times height. We just don't have the height, we have the perimeter. And so when you don't have the height and you have the perimeter, and you don't have any other methods, I mean, sometimes they have other methods where you can create a perpendicular and do it. No other methods, you can use Heron's formula with your semi-perimeter.